Hello, welcome to NPTEL online certification course on Introduction to Application of AI to Robotics. Today I am going to talk about robot kinematics, and here we are essentially going to see how can we derive the kinematics of a manipulator as well as kinematics of a mobile wheel robot. So, by the end of this lecture, you will be able to understand the concept of degrees of freedom and the role of different links and joints in a manipulator, apply the DS parameter to determine the transformation matrix for robotic manipulators, construct and interpret the homogeneous transformation matrix, perform forward kinematic analysis of a robotic manipulator, understand the model of differential drive mobile robot, and derive and apply the kinematic equation of a differential drive mobile robot. So, here essentially initially I am going to introduce the topic to you, then we will be learning about the DH parameters, the way of representing a manipulator mathematically, then the forward kinematics and the differential drive robot for that the kinematics. Okay. See, the robots are designed to perform tasks that require precise motion, positioning as well as manipulation. And the robotic system include say robot arm, which we often call as manipulator, and the mobile robots used for navigation and transportation tasks. For a manipulator, naturally the workspace is limited, but for a mobile robot there are wheels which gives the mobility to the base, okay. So, it can cover a wide range of area. Robotic manipulators consist of essentially rigid links, and these rigid links are connected by joints, and in turn they form a kinematic chain that enable controlled motion. Likewise, the mobile robot such as say differential drive robot use wheel velocities to control their motion and the navigation. Now, the study which we are going to do today, it is about the kinematics, okay. And as all of you know, kinematics is nothing but it is a study of the motion where we do not treat the forces, we do not regard the forces that cause that motion, okay. So, we are studying only about the motion. So, we essentially studying the position and its derivative, say the position derivative velocity, velocity derivative acceleration, and all higher order derivatives of the position variable with respect to time, or we could have any other variable also. Yeah. So, in using kinematics here what we try to get is we try to get a relationship between say the joint angles and the position of the end effector, okay. Say what we also called as we try to move from a joint space to the Cartesian space. Joint space means where we have all the joint angles, and Cartesian space where we want to express the position and orientation of the say manipulator end effector in the workspace. So, to describe the robot motion mathematically, as we have seen in the previous lecture, okay, we attach coordinate frames, okay, to the each link of the robot, and then we try to see the motion of that link, okay, which is attached on the robot. The study of manipulator kinematics involves among other things how the location of these frames we are assigning to the robot changes as the mechanism articulates. Why forward kinematics matters for AI in robotics? Forward kinematics, as I discussed in the previous slide, it essentially is the mapping or the relationship between the joint space and the Cartesian space, okay. So, if I have a manipulator say like this, okay, this is end effector. So, I am trying to map the relationship between these joint angles and the Cartesian location of the end effector. So, why this forward kinematics matter for AI in robotics. The reinforcement learning agents use forward kinematics to translate policy output, that is the joint commands, into the Cartesian observations. Then in imitation learning dataset, store demonstrations as joint trajectories, and of course forward kinematics map these joint trajectories into the task space, okay, that is the xyz coordinates. The motion planning algorithm which we use, or which we will be seeing in our subsequent lectures also, they use forward kinematics at every node to check for the collision geometry. Differentiable forward kinematics enables gradient based trajectory optimization and neural motion planning. That is why forward kinematics matter for AI in robotics. Not even that, the physics simulators, okay, implement forward kinematics internally for every rendering steps, and understanding of the forward kinematics is prerequisite for sim to real transfer in deep robot learning. So, because of all these features, the study of forward kinematics is of interest to us for this course on AI in robotics. Let us, before we proceed, let us try to understand one of the very basic concept in robotics, that is the degree of freedom. Okay? So, the degree of freedom of a robotic system is the number of independent parameters required to completely describe the position and orientation of a system or of an object in the space. So, how many independent parameter you need to describe the position and orientation of an object in space? That is what we call as degrees of freedom. Okay? In context of robotic manipulator which we are talking about, it represents the number of independent joint variable that can be controlled to determine the configuration of the robot. If a mobile robot is moving in a flat surface, say, it has got 3 degrees of freedom. Okay? The 2 degrees of freedom corresponding to the planar motion, where it is moving in the x and y direction, and 1 degree of freedom is about rotation, okay, rotation about a vertical axis. Similarly, I can define the degrees of freedom of a rigid body in space. Okay. So, suppose there is a rigid body in space, so it has got 3 translational degrees of freedom and the 3 rotational degrees of freedom. So, if I have to define, say, a rigid body in space, okay, with respect to a coordinate system, say here x, y and z, naturally I need the 3 coordinates to specify, say, the CG of the rigid body, as well as the 3 coordinates to specify the orientation of the rigid body. So, it has got 6 degrees of freedom. Okay. So, in a robotic manipulator, each revolute joint contribute to 1 rotational degree of freedom, and similarly each prismatic joint contributes to 1 translational degrees of freedom. Okay. And through degrees of freedom, we could say about the maneuverability of a manipulator. Okay. Before we proceed, let us describe the links, okay, because the links constitute the robotic manipulator. Okay. So, a robotic manipulator can be modeled as a rigid body, okay, connected together as a chain, and these rigid bodies are called links. Okay. So, a robotic manipulator may have connection of rigid bodies. So, say you have a rigid body here, you have another rigid body like this. Okay. So, you could have the rigid bodies, okay, and these rigid bodies are called links. Okay. And the joints, such as one here, these joints form a connection between the neighboring pair of links, okay, and constrain their relative motion. The majority of individual manipulator employ one type of basic joint type. It is either the revolute joint or it is the prismatic joint. Okay. In case of revolute joint, you have the rotary motion, rotation about a fixed axis is there, whereas in case of prismatic joint, you have the relative motion of is translation along a fixed axis. And we could have a way of numbering these links, okay, starting from the fixed base, which we assume that it is not movable. Okay. So, the immobile base can be designated as link number 0, and the first moving link can be labeled as link number 1, and so on. And the last link in the chain can be labeled as the nth link. Most industrial manipulator have 5-6 joints. Let us look at what are the various types of joint. Two I have already talked about, that is the revolute and prismatic joint here. Okay. So, here in case of revolute, you have a rotary motion about a fixed axis. In case of prismatic, you have a translatory motion, okay, along an axis. Similarly, we have a cylindrical joints. Okay. So, in case of cylindrical joints, basically we have the prismatic as well as a rotary motion, both are possible. So, it has got 2 degrees of freedom. The planar one has got 3 degrees of freedom, as I just discussed about the mobile robot. Okay. So, here also suppose if I have got a coordinate system over here. So, I could describe the position of this object by xy coordinate as well as the rotation about this axis. So, it has got 3 degrees of freedom. Similarly, the spherical one has got 3 degrees of freedom, all are revolute type. Screw has got 1 degree of freedom. Okay. Although here the 2 type of motions are involved, one is rotary and one is translatory, but here the translatory motion is linked with the rotary motion, okay, through the pitch. So, essentially it has got only 1 degree of freedom. So, here the lower pair is used to describe a joint in which the relative motion occur, because they have direct surface contact between the two bodies. Okay. Next, let us come to the Denavit-Hartenberg parameter. The Denavit-Hartenberg method provides a systematic way to assign coordinate frames and describe the geometry of serial manipulator as well as the connection between the links, okay, of the manipulator. So, essentially if you have to describe a manipulator mathematically, we can use the 4 ds parameter to describe that. Out of these 4 ds parameter, the 2 ds parameter describe the link, okay, and the 2 ds parameter describe the connection between the links. Okay. So, the 2 parameter describing the link are link length and link twist, okay, and the 2 parameter describing the connection between the links are the link offset and the joint angle. Okay. And they allow to model position and orientation of each robot link. We can systematically derive the kinematic equation, and they convert the complex 3D mechanical structure into a simple mathematical matrices, okay, through ds parameter, and that simplifies and makes our analysis easier. Okay. So, let us define the first link first, okay, using ds parameter. So, suppose this is your link I minus 1, okay, and here are the 2 axes, axis I minus 1 and this is axis I. So, the link, we can define the link length as a I minus 1, and this link length is essentially given by the perpendicular distance between these 2 axes, axis I minus 1 and axis I. These axes essentially define the joint actually, okay. And another way of defining this ai minus 1 is that suppose I have got a cylinder, okay, of variable radius, okay. So, if I increase the radius of that variable cylinder, say at axis I minus 1, okay, something like this. So, the place where it touches the axis I, that is what we call as ai minus 1, okay. And so, that is how we define the link length, and the twist I can define by again an angle. So, suppose if I have got a plane here which is perpendicular to this link length, and on that plane if I project this axis I and axis I minus 1, then the angle between I minus 1 and I axis, that is what projected axis, that is what we call as the link twist, and that is here corresponding to this figure, it is I alpha minus 1 and A I minus 1. So, that way we can define that. So, this way we define the link. Next, let us define the link connection. Okay. So, that is defined with the help of the two parameter, that is the link offset d and the joint angle theta. So, suppose this is my link I minus 1, I have got another link here, say link I. Okay, and this is the perpendicular distance between say axis I and the next axis over here, that is AI. So, this distance along axis I between this AI and say this AI minus 1, that is what we call as DI, and that is defined as the link offset. Okay. Similarly, if I draw a line parallel to this AI, okay, and I extend this AI minus 1 here, then the angle about axis I between say this one AI minus 1 and AI, that is what we call as theta I. So, this is how we describe the connection between the links. So, each link is described using 4 parameters. Okay. These parameters, as I said, are AI, alpha I, di and theta I. The AI is this parameter. Okay. So, this is nothing but link length, that is the distance from between zi to zi plus 1, okay, along xi. So, that is your AI. Okay. Then alpha I is the link twist. So, this is the angle from zi to zi minus 1 measured about xi. Okay. And then di is the link offset, that is the distance between xi minus 1 to xi here, okay, measured along zi, and similarly theta I is the joint angle, that is the angle from xi minus 1 to xi measured about zi. So, these are the 4 parameters. Okay. So, suppose if I have to describe using a matrix, okay, if I have to describe the link as well as the link connection or connection between the links using a single matrix, okay, then how can we do that? Okay. So, I can do it either 2 ways. First, say I can have a rotation about x by here by alpha I minus 1, then I could have the translation over here, okay, about along x by AI minus 1, and then I could have the rotation about z by this theta I, and then finally the translation along z by this di. And all these 4 operations, if I represent with the help of matrix, here rotation about x by say alpha I minus 1, then translation along x by AI minus 1, rotation about z by theta I and translation along z by di. If I do that and I substitute these matrices, okay, then this is what the transformation matrix I get. So, this way this transformation matrix describe a link as well as the connection between this link and the neighbor link. Okay. So, to make our life easier, there are some frame assignment rules which are made, okay, and these rules are identify the joint axis and imagine infinite line along them from the step 2 through 5 below, consider 2 of these neighboring lines. Okay. Identify the common perpendicular between them or point of intersection. At the point where the common perpendicular meet I axis, assign the link frame origin. Assign the zi axis pointing along the ith joint axis, align the xi axis pointing along the common perpendicular, okay, or if the axes intersect, assign xi to be normal to the plane containing the 2 axes. assign the y-axis to complete the right hand coordinate system, and assign 0 to match 1 when the first joint variable is 0. For n, choose an origin location and extend direction freely, okay, but generally so as to cause as many linkage parameter as possible to become 0. So, that is how we select the x axis. Okay. So, the thumb rule is that all joint rotations are assumed along the z axis, okay. The link length are assumed along the x axis, and the y axis is decided as per the right hand rule. So, that is the summary of this one. Let us take an example. Okay. So, I will first take a 3-link planar arm. Okay. So, in case of 3-link planar arm, so suppose this is my 3-link manipulator, this is my first link, this is second link, and this is my third link. So, this is my 0th frame, which is a base frame or inertial frame. This is my first frame, which is attached to the first link, okay, and their origin are also same, that of the 0th link and the first 0th frame and the first frame. At the beginning of the second link, I attach a second frame, and at the beginning of the third link, I attach the third frame. Okay, so this is my the frame assignment. Okay, so I can draw the ds parameter here. I can assume the link length, say these lengths are L1 and L2. Okay, so here these are, this is my ds table. So I have alpha I minus 1, ai minus 1, di and theta I. Okay, all z axes are parallel. So my all these alpha values are going to be 0, right. So what is a0? I is equal to 1, this a I minus 1 will become a0. So a0 is essentially the distance between the z0 and z1, right. So here since both the origin are same, so this value is going to be 0. It is a planar problem, okay. So there are no offsets, so all di's are going to be 0 here. And similarly the theta 1, so theta 1 is the angle between say our x0 and x1, okay, about z1. Okay, so about z1 here, which is perpendicular to the plane, the angle between x0 and x1, this is my theta 1. So this is my angle theta 1, right. So again let us look at this a1. What will be a1? A1 will be the distance between z1 and z2, okay, along x1. So distance between z1 and z2 here, okay, this is my z2 and this is my z1 along x1. So that is L1. So L1 is here. Similarly, as per our definition, the theta 2 will be what? Theta 2 is the angle between x1 and x2, okay, about z2. So this is my x1, so I can extend it over here, and this is my x2 and this is my z2. So angle between this x1 and x2, okay, about z2, this is my theta 2. So this becomes my theta 2, right. Similarly, I can define what is my say a2. I put 3 here in this one, so I will be getting a2. So that a2 is nothing but that will be L2, and this theta will be theta 3. Okay, likewise, and I can fill up this table. So my aim is to find out what is the position and orientation of the my end effector frame, okay, or the frame number 3 over here. Okay, so I can take this formula, right. So here I can use this complete formula, okay, and I can give the different values of i's, okay, in order to get the transformation matrix. So this T10 will be giving me this matrix, and this is, you see, nothing but rotation about z axis, okay, by say theta 1. This matrix 2 and 1, 2 to 1 transformation matrix, rotation about z axis by theta 2. This is 1, means it is a rotation about z axis. Similarly, 3 to 2, here it is going to be rotation about z axis by theta 3. And here in this transformation matrix, we will be getting this L1 term, whereas in this transformation matrix we will be getting the L2 term. Now when I substitute all these 3 matrices into this equation, this is what I get, 3 description of frame 3 with respect to frame 0. Okay. So, this is the short notation of basically C theta 1 2 3 basically means cos of theta 1 plus theta 2 plus theta 3. Okay. So, this is there, and so this matrix actually a 4 by 4 matrix. So, out of this is the homogeneous transformation form. So, this one you can see that end effector rotation is about z axis, and that is by amount theta 1 plus theta 2 plus theta 3. Okay. And these are the tip position in the x and y direction. Okay. And this example, since this example is very simple, we can get these values from simple trigonometry also. Okay. So, I will motivate you to just try this one. So, you see this position is going to be L1 cos theta 1 plus L2 cos theta 1 plus theta 2. So, this is what it is. Okay. And similarly, the y will be here L1 sin theta 1, which is this distance, plus L2 sin theta 1 plus theta 2, which is this distance. Okay. So, through this simple example I tried to explain this, the position of the tip and the orientation of the tip also. Okay. So, if I try to simulate this, let me just see here. So, in this case we have the two arm manipulator, right, the one which we have been discussing here just now. So, here this is how, if I am varying the first joint angle, the theta 1 is changing, as you can see from this example. Okay. And if I keep the theta 2 changing, then this is how it is seen, right. And I can also see the effect of the change of the link length over here. We can see that the workspace size increases say by changing L1 and L2. So, workspace size is nothing but the maximum area which this manipulator can cover. Okay. So, this way we can write a simple Python code to do the animation of this one. So, essentially here what we are doing in this forward kinematics is that we are changing these values of joint angles theta 1 and theta 2, and we are getting the different values of the x and y of the end effector. Okay, there is another example I can take, and I will demonstrate this quickly, involving a prismatic joint. The previous example which we have seen, we had all joints as the revolute joint. We have a joint which is a prismatic joint. So, say this is the joint number 1, which is the revolute joint. This is your joint 2, which is a prismatic joint, and this is the joint 3, which is again a revolute joint. Okay. These are my lengths L1 here, L2 here, and L3 over here. Okay. So, I can assign a coordinate system over here, alright. So, say my 0th frame is here itself, okay, at this point, and this is my first frame, okay, and this is the second frame, and this is the third frame. Okay. So, I can prepare the DS table similar to what we have seen over previously, alright. And then I can write the description of frame 3 with respect to frame 0, again using the multiplication of these 3 transformation matrices, that is from 3 to 2 transformation matrix corresponding to frame 3 to 2 into frame 2 to 1 into frame 1 to 0. And if I substitute those values from this DS table into the expression of which we have seen for the transformation matrix, okay, that is for the Ti with respect to I minus 1, then we are going to get these equations, okay, for 1 to 0, 2 to 1, 3 to 2. And when I substitute all of them together and do the calculation, so this is how we get the final matrix. So, from here I get the orientation matrix here, and these are the x and y position. So, to many a times we come across a doubt that whether these results are correct or not. Okay. So, to check that, we can take some values of say these joint angles, usually those angles which are easy for us to visualize, and then we can check with these results, okay, that whether it is correct or not. Next, I wanted to also discuss a differential drive robot, because in this course on AI for robotics, we are going to see at latter topics also, and I will try to integrate this mobile robot with the manipulator arm also. So, maybe I will be discussing in one of my lecture robot with a mobile base basically, right. So, with that perspective I have tried to include this one. So, suppose this is your mobile robot, there are two wheels over here, okay, and I have got a coordinate system x and y with respect to which I am describing this. So, say the CG I can describe by x and y coordinate, and its heading angle I can describe using phi. Okay. So, a differential drive robot is a mobile robot that uses two independently driven wheels placed on either side of its body to move and steer. Okay. So, it has got two independently driven wheels as I have shown here. Distance between them is 2d, this d, and then you have this d over here. Okay. Wheel radius is given, robot heeling angle is there. Then left wheel velocity I can write r into ul, where ul is the left angular velocity. So, it is basically v is equal to r omega, right. So, that will be giving the tangential velocity of the left wheel. Likewise, I can have the tangential velocity of the right wheel. Okay. So, that I can get, and here when we have the VR is equal to VL, we get a straight line motion. If VR is greater than VL, we get a left turn motion. If VR is less than VL, we get a right turn motion, and if VR is equal to minus VL, rotate in place clockwise. So, that is how we can get that. Their applications are in service robotics, automation navigation, and warehouse automation. Okay. If I want to look at the kinematics of this, unlike a manipulator arm, differential drive robot move on a flat plane. I have already discussed this. The forward kinematics map wheel velocities to the robot body velocities over here. Okay. That is the change in pose x, y and phi, where x, y are robot position in the plane and phi is the robot heading angle. Okay. So, the forward kinematics for a differential drive robot tells how the robot position and orientation changes when the left and right wheel rotate. Okay. And two main advantages of differential drive robots are its simplicity due to the motor directly attached to the axle of each wheel and the high maneuverability. So, let us look at this one. So, I can get the linear velocity of the robot center, simply right velocity plus left velocity by 2. Okay, I can write it in terms of the angular velocities, and this angular velocity will be right minus left by 2d. So, this way I can get change in the robot pose x dot will be v of say if this is v. So, v of cos phi is going to be this one, and v sin phi will be going to be this one. Okay, and phi dot is going to be basically the angular velocity. Okay. So, I can write these equations, okay, after substituting in this form, where this is my heading velocity and these are the x and y velocity. Okay. So, these things you can just do try to do it trigonometrically, you should be able to get these results. Yeah. So, this animation actually shows the forward kinematics for the wheel differential drive wheeled robot. Okay, so here you can see that for the given left wheel and right wheel velocity, we are getting the x and y direction velocity of the robot as well as the angular position of the robot. Okay, so that we are getting, and here we can see that if I make both the wheel velocities equal, then as discussed earlier, we will be getting a straight line motion of the robot. Okay. And so, this way we can play with the animation and see how these results coming. Alright. So, in today's lecture, what we have all studied, we studied about DS parameter describing the link and the connection between the links. we describe the degrees of freedom, okay, and it is a very universal known concept. I suppose everybody should know that an object in space has got 6 degrees of freedom, 3 translational degrees of freedom and 3 rotational degrees of freedom, and the forward kinematics determines the end effector pose from the joint variable. So, essentially in the forward kinematics we are mapping from the joint angle to the position, okay. And the differential drive robots, we have the independent wheel velocities for motion, and all these kinematic model enables us analysis, simulation, control of the robotic system, as well as through these kinematic model we could easily do some of the AI implementation, as I have discussed at the beginning of this lecture. So, these are the references. You can refer J. Craig as well as our book if you want to further read this topic. Thanks.